Chapter 14 introduces us to the study of fluids. Unlike a solid, where all the molecules are interacting with each other in a very strong fashion and something keeps its shape, in a fluid, the individual molecules are able to move around. They can move past each other, go around each other, and they're going all over the place, bouncing off the walls and so forth. So with a solid, we can treat it as one object because you move part of it and all of it moves. But with a fluid, that's not really the case. So with fluids, you often have to deal with what we think of as statistical analysis. And that is that you do statistical physics. You keep track of what's happening on average, not what each individual molecule is doing. You even consider, just like a little half-liter bottle of water that a lot of people drink, or even just a glass of water. You're talking there about 10 to the 23rd or so atoms you're trying to keep track of, and there's no way, we don't even have a computer capable of keeping track of that many things. So what we have to do is again find sort of statistical relationships. So what we do is we can imagine that we've got a fluid here. All these molecules are bouncing all over the place. They're bouncing off the walls, bouncing off the bottom, and so forth. Now, gravity acts down mg on the whole thing. And so these molecules that are bouncing off the bottom, for every force there's an equal and opposite force. You remember from when we talked about momentum that when they change momentum here, the change in momentum over time is the average force. So it takes a little while for them to bounce off. They change momentum, and so that exerts a force. So there has to be a total upward force of mg due to the bottom. Okay. Now, it turns out that we can't keep track of it's not like you just press at one spot and push the whole fluid. So we want to find the force over an area, and we call that pressure. So pressure, the symbol for pressure is P. I know that's the same symbol we use for momentum and the same symbol we use for power. So unfortunately, we just deal with it. So it's force per area. And so that's how we define pressure. But pressure is omnidirectional because not all the molecules are going down, they're also going in all directions. So the pressure is the same on the sides as it is on the bottom. Okay, so the pressure, force per area, the basic unit of pressure is the Pascal, and that is a Newton per square meter. Okay, so Pascal is a Newton per square meter. All right, so there we have our basic unit here. So imagine that we've got a container right here, and it's got a fluid in there. The fluid is some density rho, and I want to know what's the pressure at the bottom here. Okay, well, it's going to be mg over the area. Well, m is the mass of the fluid, so that's going to be rho times volume, g over a. Well, if we imagine this is some height h and some area across the bottom, then that would be, the pressure would be equal to rho times ahg over a. So the pressure is rho g h. So this is a relationship. In fact, we call this the pressure depth relationship. So this is the pressure depth relationship. Because there's a relationship between pressure and the depth. And that depends on the density and on G. And so that's an interesting sort of thing, because that means if you have an amount of fluid that's spread out in a little shallow pan, but have the same amount of fluid in like a test tube, the pressure down here is going to be more than the pressure here, even if it's the same amount of fluid, because it's more spread out in that case. And so this is the pressure depth relationship right here.